Okay, so 7.1 is complex vectors and matrices. So we're just going to use complex numbers in matrices and vectors. So first of all, the dot product. Everything is defined a little bit different. So we'll talk about the dot product first, because this sort of explains why. So when you do the length of something, so we said this before, so if we were finding the length of a vector, it's the dot product, square root of the dot product, and it gives you a length, it gives you a number, right? And complex numbers, the length would also be a number. It can't be a complex number. It has to be a size, like a measurement. And if I did a dot product in the way that we might think for a complex number, so for example, if I had like z as a vector is equal to 2 minus I and 1 plus I, and w as I and 6 minus 2I. Okay, so we've got two vectors, just a column vector with two, right, a 2 by 1 vector. If we were to take the dot product of these, do we end up with complex numbers or not? What do you think? Well, let's try. So what would we do for a dot product? I'm just going to write this as wrong first before we do it. Okay? Because we're going to remember that it's not this way. But what we would normally do is multiply the first two and then add the second two. And remember, the dot product always gives you a number as an answer, not a vector. The cross product gives you a vector, but the dot product gives you a number. So we would do 2 minus I times I plus 1 plus I times 6 minus 2I. Okay? So this is the normal way to do it, but when there's complex numbers in it, this is not the right way. So we actually have to change something first. But if we work this out, 2I minus I squared, right, I just multiply that, plus 6 minus 2I plus 6I minus 2I squared. And what's I squared? Minus 1. So what do we have? 2I plus 1 plus 6 plus 4I plus 2. 6, 7, 8, 9 plus 6I. Okay, so that's actually not the way to do it, but you can get a complex number as an answer. Okay, but this would not be a length. Well, that's dot product with itself, but so it's not a length. It's not a single number like a regular dot product. You can get a complex number. This is the wrong way to do it. The right way to actually do a dot product is this. So dot product in complex numbers is z dot w, and in the complex plane would be z bar dot w. We have to change one of them. Okay. So what this does is when we're trying to find a length, it will actually give us a number rather than a complex number. In regular dot product, this could still give us a complex number, but it can't be a length. Okay. So what am I saying? I'm saying if we wanted to find the length of the vector okay, and the normal way to find the length would be u dot u and take the square root of that. But if we do that, just like we did here, when you do a dot product, you can get i's in it. and then it's a complex number and it's not a length. So the way to change that is to do the conjugate, and then the dot product that way. So we would do 2, so the conjugate of this would be changing all the signs in front of the I, so 2 plus I and 1 minus I, and then dot that with the original. And then that will give you a number. Okay, so if we work this out, so 2 plus I times 2 minus I, plus 1 minus I times 1 plus I. So this gives us 4 minus 2I plus 2I minus I squared. These cancel. So this is 4 minus a minus 1 plus 1 minus a minus 1. And we did that last class. When you multiply a complex number by its conjugate, you get its length, which is just a squared plus b squared. Right? In just a complex number. Here it's a little different because it's a vector. Okay, so that would actually be the length. So anytime you multiply, you convert one to the conjugate. So, if we wanted to say, an example might say this, show that z equals 2 minus I and 1 plus I, and W are orthogonal. So how do we show that two vectors are orthogonal or perpendicular? The dot product equals 0. So we need to show that the dot product is equal to 0, but since they're complex, we have to do it this way. And usually they take the dot out when they show that, the complex, but if you put it in, it won't be wrong. But it's usually the dot product is equal to z bar times W, written without a dot in between. So you take your z, the complex conjugate, and you're going to dot that with W, and hopefully this equals 0. So 2 plus I times 6 plus 8I plus 1 minus I, 9 minus 13I. And 2 times 8. 9 minus 13I minus 9I plus 13I squared. So 12 plus 8 times minus 1 plus 9 plus 13 times minus 1. And, whoops, 16I plus 6I minus 13I minus 9I. Alright, so what do we have? Do we have 12 minus 8 plus 9 minus 13? Is that 0? Yep, 0. And is this one 0? Yep. So 0 plus 0I, which is 0. Okay. So you have to remember to do that. So when this is like multiplying matrices, So to multiply matrices, A times B, they would write this as A star B. I don't know why they put a star instead. It's the conjugate. They don't put a bar over it though, they put a star. Where A star is the complex conjugate. Okay, so if we were asked to find AB and BA, so to do A times B, we do A star times B. So A star is changing all the complex numbers to its conjugate. So it would be 2 minus I, 3 plus 2I, minus I, and 5 stays a 5. There's no imaginary number in there. So this is the conjugate of A. And then we want to multiply that by B, and you don't change B. Okay, and multiplying is doing a whole bunch of dot products, and that's why this rule applies here too. So you're doing the dot product of that vector with that vector for our start. So 2 minus I times 1 minus I plus 3 plus 2I times 2. So that would be our first number that will go right here. Minus 3 plus 4 is plus I, so 6, 9, 9 plus I. And then you would do your next one. So stay with the top row and multiply by the second row. So 2 minus I times 0 plus 3 plus 2I times 3I. So this is 0. 9I plus 6I squared is minus 6 plus 9I. And so on. So the next one, go to row 2 with column 1. So minus I plus I squared plus 10. So that would be 9 minus I. And then our last one, 15I. Minus I times 0 plus 5 times 3I. Okay. Now, you would do the same thing if we wanted to find B times A, but you conjugate B instead. So whatever one is first is the one you switch. Okay. So this would be 1 plus I, 0, 2, minus 3I. And then you would get your answer, same way. Different answer. Okay, and where we usually see this is eigenvalues and eigenvectors. So, for example, find the eigenvalues and vectors of A. Okay, so this doesn't start with complex numbers, although it could. So, how do we do this? So a little review of eigenvectors and values. What do we do first? We need the determinant of A minus lambda I. So we need to subtract lambda from the main diagonal and do the determinant. So here the determinant would be minus lambda times minus lambda, and then backwards, minus 1 times 1. Lambda squared plus 1. Set that equal to 0. And there's no such answer as there is none. So that's why we need complex numbers. So lambda is plus or minus square root of 1, negative 1, which is plus or minus I. All right, so those are the eigenvalues. How do we find the vectors? Plug I into the matrices and row reduce. Yes, row reduce with I's in there. But remember, eigenvalues and eigenvectors are easy to row reduce because it's always infinitely many solutions, so they always work out nice. And they still will, but sometimes it's a bit tricky. So we have our I'll put just the positive I in first. So minus I, minus 1, 1, minus I. Augment that with 0, and we need to row reduce. So what might be our first step here? I would switch, because dividing by I, you have to multiply the top and bottom by its conjugate, right? So I would switch row 1 with row 2. And we do this the same way as like when we had letters in it. The only difference is I squared is negative 1. So when you get that in your answer, you convert it. So here we want this to be a 0. It's in row 2. It's a negative I, so the 1 needs to be a positive I. So I times row 1 plus row 2. So you'll have to do I times everything in row 1. So I times 1, I times minus I, and I times 0. So this will be I. Minus I squared would be a plus 1, because this is minus a minus 1, and 0. So this is my I times row 1, and my row 2 and that's what we wanted to happen, right? So 1 minus I, 0, 0, 0, 0. So we write out our solution. So this is x and y. So x is the lead, and y is free. So x minus I, y equals 0, and y is t. So x equals I times t, and y is t. Okay, like I is like a number, like a 2 or something. And then our second one should work out as well. If we put negative I in, so our vector's up here. So minus I is I, 1, and I. Same thing, switch them. Row 1, switch with row 2. And these 2 by 2s work nice because it always has to have a row of zeros and there's not much option. If it was a 3 by 3, it's a little bit more complicated, but so this is in row 2. It's a positive I, so the 1 needs to be a negative I. So negative I times 1. Negative I times I would be positive 1 and 0. I minus 1, 0. . So this would be x plus iy equals 0. So x equals minus iy, or minus it, if you want. So factor out the t, minus I1. Looks okay. So if I'm going to give a 3 by 3, but it's really easy. But the row reduction, I think it's better to show you one more. So if we had A is 1, 0, 0, 0, 0, minus 1, 0, 1, 0. Lots of zeros to make it really easy. Okay? And we want to find the eigenvalues. 1 minus lambda, 0, 0, 0, 0, whoops.
0 minus lambda.
Yeah. Hopefully you guys are in pencil, you can fix that. And minus 1, 0, 1, minus lambda. And we want the determinant of that. So it's a 3 by 3. I'll do it the diagonal way. So 1 minus lambda, minus lambda, minus lambda. That's here. Then that one would be 0 and this one would be 0. Backwards, 0, 0, and not 0. So minus 1 minus lambda, 1, and minus 1. All right. So how do you factor this? Don't multiply it all out or you get a cubic. There's only two terms. Do they have something in common?
1 minus lambda.
Yeah. So 1 minus lambda. What's left here is lambda squared. Lambda times lambda. And that came out, so this is left. Minus a minus 1, so plus 1. So here, we get lambda equals 1. And here, what do we get? Right, plus or minus I. So those are our 3. So let's do the eigenvectors for one of the I ones. Okay? This one will be, I mean, they're all pretty easy. There's tons of zeros up here. I'm just going to rewrite this without all the lines on it. So if we plugged in lambda is I. So 1 minus I. Zero, zero, zero. What's our first step? We need a 1 in that top corner, and this time I don't have one to switch. So you do have to divide by. Pretty easy though, right? But let's say there was a number there. How do you do this? Do you remember? So if we needed to do, say there was like a number here, a 2, and we needed to divide it by 1 minus I. How do you do that? Remember last class we multiply it by its conjugate, right? So you would actually get that number. So this would be 2 plus 2I, and on the bottom we would have 2. It would be 1 squared plus 1 squared. 2, which would be 1 plus I. So if that were there, then you would have that in your place. Now we've got all zeros here, so row 1 is equal to row 1 divided by 1 minus I. But anytime you have something, if you divide it, you actually have to figure out your complex number to put there. Okay, you don't leave it as a fraction. All right, so what would be next?
Switch 2 and 3.
Yeah, I would switch 2 and 3 to get a 1 in that spot. And then when we do the next step, that should end up giving us a row of zeros. So our next step would be here. This is in row 3. It's minus I, so that needs to be a positive I. So I times row 2. I times 0, I times 1, I times minus I. Is 1. And then add row 3. Okay, so we get a row of zeros, which is what we wanted. So we get x equals 0. We get y minus I z equals 0. And so z would be free. So x equals 0, y equals I times t. When you move it over, it becomes positive, and z equals t. Do you see it? So you can do everything in complex numbers. You can have matrices with complex numbers in it, or matrices that end up giving you eigenvalues that are complex numbers. That's just for the first one. If we wanted to find them all, you would go through and find them all, but it's pretty similar. The only difference is when you do that dot product or matrix multiplication, you do the conjugate of the first one. That's the only difference. Okay, so I think that's it. So what we'll do next time is the review. So for the review, basically I'm going to list a whole bunch of topics that you need to find and study. So a big list of possible questions, basically. Every possible question I'm going to list. So a big list of possible questions, and I'll give you little ideas on each of them. Okay, I'm not going to reteach the course in 2 hours, but I'll give you a list, then you can go back and say, okay, do I know how to do this? Do I know? So sort of a checklist to study from. So that's what we'll do next class. And